Okay, so I'm here to talk about a very new piece of work that we've been doing at MIT. Key points. This is very early work. We started running active samples exactly 2 months ago. I started running lithium less than a month ago. Our observations are consistent with the conjecture of secondary disintegration by excitation transfer, and that we expect to see different energies coming out of the system than you would expect from DD fusion. So our methodology is load metal matrices with hydrogen and or deuterium ions in an ion beam system. One of our main objectives is replication or getting further data from a Lipinski-like setup where they've observed a different energy level than is expected from DD. Okay, so here's our equipment. We've got a high UHV vacuum system. We're able to hit 10 to the minus 9 torr, roughly, background. I've got vacuum gauges. I've got particle detectors in it, SSB particle detectors. And then we're running a Wendy neutron detector, 3HE neutron detector, titanium and lithium. Gas flow is being done in a very, very ad hoc way. We don't have high quality, expensive leak valves into our system. Okay, this is the design of the system. This is as we initially started building it up. This is our ion beam. This is from Oxford Applied Research in the UK. This is the system built up as a whole. We've got the ion gun in the left-hand side of the system. We've got a data acquisition system located right here in a Raspberry Pi. We've got somewhere up there, there's a hydrogen deuterium sensor so we don't get caught by a leak in our systems and blow ourselves up. And then this is operational. This is a titanium sample with the beam running. We found as soon as we turned the instrument on that FedEx had damaged the electronics that it was shipped with, so we had to build up our own electronics. And that's there. This is our Ortec for the charge particle detection. And now we should be moving on to, this is something that we have coming in soon. This will be better charge particle electronics, lower noise, higher capability. We're planning on adding a particle telescope to our system, so this will be better for analyzing data coming from that. And then this is our Wendy, which is strapped to the side of the neutron detector, strapped to the side of the experiment chamber. These are calibration plots. This is the full plot, all the above the noise, all the detection from our A series detector and our R series detector, our chosen lines for the center calibrating against americium. So this is how we calibrated our detectors. Now, we are looking very explicitly for excitation transfer. You've already been through this several times. I'm going to skip through these pretty quickly. We consider that the energy available isn't really above 3.6 MeV. We're looking for things that come from higher energy levels out of excitation transfer. And Peter has modeled this for lithium. We think this matches Lipinski. And then palladium and 21 MeV would match the Chambers et al. From 1990. And there's their small number of counts, but that's their observation. And this is Peter's calculation of the energy available according to mass number from different elements. So these might predict what elements we were seeing transfer from. All right, so this is now into the plots. This is one of our early experimental runs. Our target was to run against titanium. We were running at 950 electron volts. We ran for 1.5 hours, targeting 50 microamps, and then 3 hours at 150 microamps, then switched to argon and turned the current up. Actually, I guess I turned the current up very briefly while I was still running deuterium, and you can see that there. So the intention of switching over to argon was to add some phonons to the system, to see if we could put a little physical force into the system. And sure enough, within a few minutes after turning on the argon, we see, coincident within a couple of minutes, a neutron peak on the Wendy detector. I haven't done an analysis on this, but this is so far above background that I have no doubt that it's significant, and we will be going back to replicate this. And then in the same roughly 3-minute period, we have charged particles, and these are all measuring in the range of 30 MeV, which isn't something we expect to come from titanium. To the best of my knowledge, correct me if I'm wrong, Peter, you're thinking that there's some other impurity that might be responsible for that.
Yes, something very high Z.
High Z, yeah.
Uranium.
Yeah.
Thorium, something like that.
Yep. Okay, so we were happy with this. None of the other experiments seemed to benefit anything until I went back and looked for the data that I saw, looked for things similar to what I saw here. These are by no means replications, but we had, let me touch on this first before I move on to the next experiment. Right in magnifying this section right here, and you can see where the charged particles were noted here. My measured ion current off of this is ion current measured off of the target, starts to have these fluctuations. I have to think that these are associated with whatever was happening in the sample when whatever happened in the sample. I have absolutely no explanation for what they might be. This is magnified a little more, and to step back quickly, this line right here has to be electrical noise. It's a single bit, a single data point. There is none of this physical effect peak that you see here, but the rest of these look like some sort of a real physical effect, and they don't square to anything else that I was measuring. They don't square to my current, to my gas flow. They don't square to my vacuum. I looked at my vacuum pressure. That's a question that I've got outstanding. Okay, so as I said, I went back and I looked at prior work for anything that might be a small correlate, because I knew I didn't have any big ones. And this is virtually the very first experiment with titanium. And after I was done running the experiment, by a couple of hours, there's a pretty sizable neutron peak, not as big as the one that I showed in the prior slide, correlated within a couple of minutes with a 6.6 MeV charged particle. So not really knowing what's going on there, but because they're so closely correlated in time, I got to think that there's something going on there. Okay, then looking at a next, and I'm sorry this slide is rather hard to read. I didn't have a chance to rework it. This was an experiment in which we ran on deuterium for a good long time, let the system sit and begin to degas to let the implanted deuterium, which was fairly deep in the surface, start to come out, then start to run deuterium again and start to run argon. So a similar experimental protocol to the July 10th that I showed earlier. And during this time, and again, this guy is completely unexplained, but he's in the right EV to match my July 10th result. And then soon after I've switched over to argon, we see roughly 30 meg EV charged particle peaks. Again, this is not by any means replication. We'll be going back to look at this, and we haven't looked at it in the meantime because our charge right now is to work on lithium. So we don't have a replication of Lipinski yet, and these slides will not be very detailed, and I'm showing different axes here. I've got my ion current, and then I've got my system pressure. The behavior that I saw as I was running this, I will say as a convenience and being nice to my equipment, I was running my backing pump in its low speed because it was keeping up with the system pressure, and there was no apparent benefit. And then I saw this happening. So my system pressure is going up, my current is going up with it. Turned my backing pump back up to its full speed, continued on, and then it started doing the same thing. Now this is the third time that I ran an experiment like this, but this is the most interesting one of the bunch. At this point you can't really see it, but I'm working to control that rise using both my filament current on my ion beam, and when that wasn't sufficient, then I was also tweaking down my gas flow into the ion source to try and keep it in control while letting something happen. So by this time we had added an RTD sensor, and here is the temperature profile. So this is the temperature as this experiment was running. This RTD is sandwiched in between the lithium and the copper backing that is used for both holding and conducting electricity out of the system, or current out of the system, I should say. And so what I think is happening here is, while we're still at relatively low temperature, we're loading our system up with a fair amount of, and we're running hydrogen in this experiment, by the way, not deuterium. We're loading it up with a fair amount of hydrogen. Temperature begins to go up, and the lithium begins to evolve the hydrogen, and it evolves it at a rate that is swamping the ability of my vacuum pumps to pull it off. I turn the pump up, run longer, it now swamps the ability of the pump even with the backing pump running at full speed. So this so far has just been well, we saw some heat. We don't really think it's excess heat. However, I want to draw your attention to some very well correlated spikes in pressure and ion current that are happening here. Again, there's no other input to the system in this that's causing those to be well correlated, and I don't have a physical explanation for why that's dynamic, why it's not simply ramping up slowly. So that's something to go back and look at. One of the biggest things we'll be doing toward that is improving our heat transfer out of our sample. I think what we're going to do is melt the lithium onto the copper target for perfect or very good heat transfer out, and then we will be able to control the temperature, avoid these spikes, and do higher loadings and also get better thermal measurements. Okay, so that's that for that slide. Okay, so ongoing work. We are principally focused on lithium, Lipinski and Lipinski. Palladium is high on our list, returning to titanium and trying to replicate that result that we had on July 10th. And then these are additional target materials that we're especially interested in and will be running soon. System upgrades. We need proper leak valves so that I'm not having to tweak the valve every few minutes to keep the ion system running right. We want larger charged particle detectors, a charged particle telescope, an IR camera to measure our temperatures, and I'd like to replace our rad film with beryllium shields. Temperature control and cooling on the target stage is also important, and then we are looking at how to increase both the current and the potential EV available from our ion beam system. That's pretty much that. Thanks for your attention.
I was going to see if you've thought to try to correlate the jumps and jags you're seeing in those parameters with something like acoustic or vibrational noise.
I certainly would, and I will when I can do that. Getting an acoustic transducer, getting every transducer into an ultra-high vacuum system is a task. So everything we add has a significant cost.
Many of the features you're seeing there are very reminiscent of things that I've seen looking at gas loading with a high resolution measuring the resistance changes.
Cool.
And so that turned out to be extremely sensitive to vibrational input. And there were regions of instability in those what I was seeing that was dependent upon the loading. So there were areas where there was no sensitivity, essentially, and areas where there was just extraordinarily high levels of sensitivity.
We can look at, yeah, we probably will look at that. Thank you.
I just missed. You measure the charged particle spectrum,
Yes.
and you saw the very high energy charged particles.
Yes. Yeah, on our calibration, between 29 and 33 MeV.
So something around 30 MeV, you said.
Sorry?
30 MeV.
30
Yeah.
meg electron volts, yes.
So what kind of particle are you thinking about?
I would be saying we're calibrated for alphas, and we haven't calibrated for anything else. I don't have the slightest, please, Peter.
Yeah, I was going to point out, at some point, we're going to have to get into an accelerator to get a calibration up at that high of an energy. But the excitation transfer, if you have 24 MeV and you do an excitation transfer up at very high Z, going all the way up to uranium, the alpha will come out somewhere near 30 MeV.
Oh, did you talk to the Lipinskys, and if so, what was the best advice or insight you got?
I did talk with the Lipinskys, and I did get some input. However, now that we actually have a vacuum chamber and we have a little bit of experience under our belt, I think we got to go back and do some more talking. One big piece of input that is evident in retrospect from their documentation is the need to cool the lithium sample. At the moment, the lithium's not particularly well connected to the copper, and we obviously have a temperature issue that we're going to have to solve before we can get into a regime that's relevant to the Lipinski experiment. The experiment number 13 or something, which is the one we're focusing on.